Hello students! Chalo, let's start a very important topic from our chapter on moving charges and magnetism. Torque on a current loop. Now, I know this topic can seem a bit tricky, but don't worry. We're going to break it down so simply that it will be crystal clear, not just for your exams, but for good.
Okay, to get our brains warmed up, let's start with a little mystery, a question about things we see around us.
So, what is this invisible force that makes a compass needle point north, or a motor spin? That turning force, that torque, is exactly the mystery we're going to solve today.
Now, here's a secret that will make this topic much easier. You've actually already learned something very, very similar. Remember Chapter 1, electrostatics? We're going to connect back to that. Look, on the left, you see an electric dipole in an electric field. It twists, right? Now look at the right. A current loop in a magnetic field does the exact same thing. This parallel, this analogy, is the master key to understanding everything that follows. If you understood that, you will for sure understand this. Okay, so for our exams, the most important thing is the formula. Let's look at the exact formula for this turning force, or torque, as it's given in our NCERT textbook. Here it is from section 4.9.1. Torque, or tau, equals I/AB sine theta. So the turning force depends on the current, I, the area of the loop, A, the magnetic field strength, B, and crucially, the sine of the angle, theta. And remember, theta is the angle between the magnetic field and the normal to the coil's area. That is, a line sticking straight out, perpendicular to the loop's surface. That part is very important. Now, to make our lives easier, physicists combine a few of these things into one term. It's called the magnetic dipole moment, or M. For a single loop, it's just current times area I. But if the coil has N turns of wire, as shown in the formula here, it's M equals NIA. Just think of M as a measure of the loop's overall magnetic strength and its direction. And with that simple substitution, our main formula becomes so much cleaner. Look at that. The torque is simply mb sine theta. And if you remember your vectors, it simplifies even more beautifully to a cross product. Torque equals m cross b. Much easier to remember, isn't it?
But just memorizing the formula is not enough, right? We really need to understand where it comes from. So let's quickly derive it. Tension mat lo, it's actually based on very simple logic. So just imagine we have this rectangular loop placed in a uniform magnetic field. There's a current I flowing through it. Now, to understand the torque, we need to analyze the magnetic force that's acting on each of the four arms of this loop. Now think about the two vertical arms. If you apply Fleming's left-hand rule, or the vector formula F equals IL cross B, you'll find that the force F1 on one arm pushes inwards, and the force F2 on the other arm pulls outwards. They have the same exact magnitude, I times B, but they are in opposite directions. So what about the top and bottom arms? Well, the forces there are also equal and opposite. But, and this is the crucial difference, they act along the same line, which is the axis of the loop. So they just pull on the loop and cancel each other out perfectly. There's zero turning effect from them. But now let's look at the loop from the top. You can see that F1 and F2 are not acting along the same line. This pair of separated opposing forces is what we call a couple. It's just like turning a steering wheel with both hands. One hand pushes up and the other pulls down. This couple is what produces the turning effect, the torque. Okay, let's put the math together. We know torque is just force multiplied by the perpendicular distance between those forces. The force on one arm is F equals IBB. Now, look at the diagram. The perpendicular distance between the two forces is A sine theta, so we just multiply them. Torque equals IBB times A sine theta. And since A times B is just the area, A, of the loop, we get our final formula. Torque equals IAB sine theta. See? Simple, right? Let's quickly plug in some easy numbers. Suppose the current is 2 amps, the area is 0.5 square meters, and the B field is 3 Tesla. If the angle is 90 degrees, sine 90 is 1, so the torque is maximum. It's just IAB, which is 2 times 0.5, that's 1, times 3, giving us 3 Newton meters. See? It's that simple.
Right, now for a very, very important section. Let's talk about the silent killers. You know, those common mistakes that can cost you marks in the exam if you're not careful. So think back to all 4 forces we talked about, F1, F2, and the 2 forces on the horizontal arms.
What happens when you add all of them up as vectors? What is the net force?
That's right, it's zero, a big fat zero. All the forces cancel each other out. This is a critical point. The loop does not accelerate left, right, up, or down. It only rotates on the spot. Please, please remember this for your MCQs.
Okay, so the net force is zero, but does that mean the net torque is also always zero? Be careful here. No, the torque is not always zero. As you can see from the formula, it's maximum when the loop's plane is parallel to the field, when theta is 90 degrees. It only becomes zero when the loop's plane is perpendicular to the field, when its magnetic moment, m, lines up perfectly with the B field. This is the position of stable equilibrium.
ठीक है, let's quickly wrap up. We will summarize the key points and see how this topic connects to the rest of magnetism.
So, to summarize, first, a current loop in a uniform B field feels zero net force, but it does feel a torque. Second, that torque is given by the cross product M cross B. Third, we define the magnetic moment M as NIA. And finally, all of this means a simple current loop behaves just like a small bar magnet. Keep this slide in mind for your final revision. And that leaves us with a fascinating final thought. If a current loop acts like a magnet, could it be that all magnets, even a simple bar magnet, are actually made of tiny, microscopic currents flowing inside? This amazing idea, first suggested by Ampere, is actually the foundation of modern magnetism, and we'll explore it in the next chapter.